Hello, I'm Kushal Sharma. I will be explaining two papers today. These papers are based on large language models and their planning capabilities. The first is the Plan-Seq-Learn language model guided RL for solving long horizon robotic tasks. And the second one is grounding LLMs for robot task planning using closed loop state feedback. The first paper involves a combination of LLM and reinforcement learning to perform long horizon robot related tasks. What are long horizon tasks? Long horizon task is a fancy way of saying complex tasks which can be broken down into smaller subtasks and can be solved individually. In robotics, long horizon tasks are quite common, but tackling those is a hefty problem. Just like what can be seen here, we have a robotic arm whose main goal is to place both color nuts on the screws. This is termed as a complex or long horizon task, and can be broken down into the following smaller tasks like pick up gold nut placed on gold screw, and same for the white nut too. But what is the need to combine large language models and reinforcement learning for this purpose? Both of the mechanisms have their own pros and cons. LLMs are good at breaking down complex tasks into smaller ones, but they fail to devise low-level strategies, especially for robot-related executions. On the other hand, reinforcement learning can devise strategies to perform these robotic related executions, but they fail to do long-term reasoning. Plan-Seq-Learn approach uses LLM for high-level policies and guides RL for low-level control. This approach has demonstrated uh, 85% success rate and solves 25 plus long horizon tasks. This approach can be broken down into three major modules. The first is the planning module, the high language plan of the complex task, which is revised by LLMs. A sequencing module, the execution part of the process, which essentially incorporates motion planning. The third part is the RL policy to learn control strategies for small tasks. The approach provided by the authors considers partially observed Markov decision processes. Here we have a detailed outline of the architecture used. The LLM is provided with a long description of the task at hand, including the termination condition and formatting in the planning module. The LLM here then outputs a sequence of steps that must be followed by the robot to execute the given task. The authors tried a number of different LLMs, but concluding that GPT-4 was the only one that gave correct plans for the type of tasks that they were considering. They also mentioned that they took care of any LLM hallucination that might have occurred. The plan generated here has multiple stages, which are then forwarded to the sequencing model. But what do the prompts and generated plan look like? The authors here employ a specific prompt and plan style. The prompt fed into the LLM is composed of three elements. The first being the stage termination condition. This is a predefined set of conditions that signify the completion of stage or step. It can be also viewed as the action to be performed in the step. For example, grasp, place, etc. Next comes the task description. It is the main or the complex aim of the robot which is to be completed. It is written in natural language description. For example, the gold nut goes on the gold peg and the silver nut goes on the silver peg. The last component of the prompt specifies the output formatting. It provides the LLM with an explicit format that must be followed while providing the for the planning task. The format required is a list of tuples where each tuple contains target, region, or object and stage termination condition in this order. Some examples of the prompt are generated plans can be seen here. After receiving the broken down steps or plans from LLM, the sequencing module determines the robot's poses for movement. This module consists of two main components, vision estimation and motion planning. The vision estimation part uses two calibrated depth images of the scene to generate a global view. These images are processed to segment both the robot and the target object using a segmentation model, which can be segment anything model. The segmentation provides masks for robot and object, which are used to estimate the 3D position of the target object. This 3D position is then converted into a target robot pose using inverse kinematics. Motion planning is then employed to use which uses the target pose which is estimated to compute a collision-free path for the robot to reach the target from its current configuration. The motion planning is performed using sampling-based planner AIT star, which ensures efficient path finding by checking for collisions with objects in the scene. The sequencing module then kicks things off by processing uh, visual input into the robot or to specific region of interest identified in the plan. Once the robot reaches the spots, the learning module takes over, handling the detailed control tasks using reinforcement learning. For this, PSL leverages DRQ version 2, a model free visual RL algorithm. This system operates directly on image inputs, generating precise low level control actions. What makes PSL stands out is instead of training multiple policies for different task stages, it uses a single IL policy that works across all stages. This policy operates locally, focusing on the area right around the robot, which removes the need for a global view of the entire scene. Stage transitions like grasping or placing are identified through visual pose estimates, and training is guided by environment-specific reward functions. Policies are trained using a compact 84 by 84 pixel image inputs, and an exploration schedule gradually improves efficiency over 500,000 steps. PSL was tested in four simulated environments: Meta World, Obstructed Suite, Kitchen, and Robo Suite. Tasks range from simple ones like lifting cubes and assembling nuts to complex multi-stage challenges such as opening cabinets or turning knobs. For example, in Meta World, the robot performed tasks like disassembling a nut from a meg or hammering a nail, while the kitchen suite focused on long horizon tasks. To measure PSL's effectiveness, it was compared to other methods, including learning-based approaches like E2E, which employs DRQ version 2, and hierarchical methods like RAPS. The vision-based systems like SECAN and TEMP. Importantly, all methods use visual inputs, but PSL stood out by integrating both global and local observations. Uh, PSL achieves impressive results, successfully completing over 85% of long horizon tasks, even those with up to 10 stages. For example, it scored a 96% success rate on challenging nut assembly tasks compared to other approaches. E2E and RAP struggled with long horizon tasks due to their reliance on global scene views or rigid subroutines. SECAN, which uses a fixed skill library, lacked PSL flexibility to adapt to new scenarios. It also MOPA RL, which also combines motion planning and reinforcement learning, was less efficient since the RL agent had to decide when to call the motion planner. PSL's strength lies in the ability to initialize RL policies near region of interest predicted by its high-level plan. This approach ensures efficient learning of local interactions, significantly boosting sample efficiency. The team also tested PSL's robustness by introducing noise into the robot's pose estimates. Remarkably, PSL maintained a 100% success rate for noise levels up to 0.025. Even at zero point 0.1, it achieved 75% success rate, demonstrating resilience to moderate inaccuracies. However, at extreme noise levels like 0.5, performance dropped to 0%. For comparison, say can saw a much sharper decline, dropping to just 27% success at only 0.02 noise. Next, we go on to the second paper. This paper proposes a new approach for devising robot plans. It employs a state-of-the-art LLM model that has general data to compute the plans required to execute robot tasks. The author proposed a framework called Brain-Body LLM. This serves to address some problems faced by LLMs while devising feasible plans for robot-related tasks. Grounding refers to connecting LLM generated plans with real world environments. This is essential for improving robustness of LLMs in robot task planning. Incorporating environmental feedback allows robot to resolve errors in real time, enhancing their ability and success rate. Authors to this paper tried to address some problems which are generally faced while using LLMs to solve uh, robot-related tasks. Problems addressed were LLMs often produce hallucination, that is, the plans are not executable in real-world environments due to physical constraints. LLMs may miss critical steps required for task completions, like switch on microwave when making coffee, which is essential for making coffee. Robots need time to adapt to dynamic environments and refine their plans based on real-time feedback to ensure successful task execution. The brain LLM is like the planner in this whole system. It is responsible for taking a task, let's say something like make coffee, and breaking it down into a series of high-level steps that the robot can follow. These steps can be pretty straightforward and sequential, like walk to the fridge, grab milk, and so on. The key functions include it decomposes a task into smaller manageable steps. For example, making coffee, it might generate just it is also aware of the environment, meaning it knows what objects are available and their states, so it won't tell the robot to grab something that isn't there. It also uses common sense reasoning to ensure that each step logically follows from the previous one. This makes sure that everything flows smoothly. The second part here is the body LLM. Now, once we have this high level plan from brain LLM, we need something to actually execute it. Here's where body LLM comes in. It's responsible for taking each high level step from brain LLM and converting into low level commands that the robot can understand and act on. It basically translates each step into specific actions. So if brain LLM says grab milk, body LLM will generate something like grab space milk, a command that the robot can directly execute. Uh, if a step can't be executed, for example, if there is no milk in the fridge, the body LLM will output a special sparse token. This tells the system to skip that step instead of getting stuck or making errors. Then we finally have the feedback loop, which is super important for making sure everything runs smoothly during execution. If something goes wrong, like an action fails, the system does not has to stop. Instead, the feedback is sent back to the brain LLM so it can update the plan and try again. This error message is if an error happens during execution, like maybe an object isn't there where it's supposed to be, the system detects this and generates an error message. This error message is then sent back to the brain LLM, which updates its plan based on what went wrong. The cool thing is that brain LLM doesn't start over from scratch. It just fixes what it needs fixing and continues from there. This process repeats until either all errors are resolved or we hit a limit on how many feedback loops we allow. Uh, for an example, let's say the robot tries to place food in microwave, but the microwave door is closed. The feedback loop kicks in and sends this error back to the brain LLM. The brain LLM then updates the plan to include open the microwave door before trying to place the food inside. Let's look at the prompt templates that we will be using for each of the uh, three different components. The planning prompt, which can be seen here, is what gives the brain LLM all the information it needs to break down a high level task into smaller manageable steps that the robot can actually perform in its environment. The first task instruction is basically the high level task that we may need to complete, like make coffee. The brain LLM will take this and figure out what all steps need to be, what all steps must be needed to get this thing done. Then we have environment information, which tells the brain LLM about the current state of the environment. For example, it might say the microwave is off or the fridge is closed. The brain LLM uses this info to make sure its plan fits with what's actually happening around the robot. Then we have available actions. Here we provide a list of actions that the robot can perform in this specific environment. It could be like open fridge, grab milk, turn on microwave, or anything like that, like these. Then we have some in-context learning examples. We also give some examples of tasks and the step-by-step plans to help the brain LLM to learn patterns. These examples guide it in generating plans for new tasks that that hasn't seen before. This is just like a few shot learning, which we employ in prompt engineering. Next, on the prompt templates, we have the execution prompt. This is used by the body LLM. Now, once the brain LLM has generated those high-level steps, we need to convert them into actual commands that the robot can follow. Uh, that's where body LLM comes in. It takes those natural language instructions and turns them into specific actions that can be executed by the robot. Large language steps. These are the high level instructions from the brain, like grab milk. Then we have available actions and objects. Just like with brain LLM, body LLM also needs to know what actions are available and what objects are present in the environment. This helps it figure out how to carry out each step. Then we also have in context learning examples, like we did in the previous brain LLM template, using the few short method to make the LLM understand better what needs to be done. Finally, we have the feedback prompt. Uh, this kicks in when something goes wrong during the task execution. If an error happens, like if an action fails, the feedback prompt informs the brain LLM about what went wrong and asks it to update its plan accordingly. The feedback prompt consists of an error message. This describes what went wrong during execution. For example, the microwave door is closed. Could be an error message if the robot tried to put something in but couldn't because the wasn't open. Explanation of error. This part provides additional context about why things went wrong. It helps brain LLM understand what caused the failure. Then we have the updated plan requirement. Here's where brain LLM gets to work on fixing things. It's instructed to generate a new plan starting from where the error occurred. So it doesn't have to start over from scratch, but picks up from where things went wrong. Like all the other templates, this also needs in context learning examples uh, for the few shot learning approach. Now, how this brain body LLM approach was tested. The experiments were carried out in two main environments, the virtual home simulation and the real world test, using a Franker Research 3 robotic arm. The virtual home setup is a simulator that mimics a household environment where robots can interact with objects like fridge, microwaves, and more. These objects have different states such as open or closed when the robot has to deal with. The system was tested on 70 different tasks, all centered around typical household activities like make coffee, eat chips on sofa. The simulator provided real-time feedback on whether the robot's actions were successful or not, which triggered the feedback loop in uh, brain body LLM to adjust the plan when needed. Next was the real world setup. For the real world testing, they used the Franca Research 3 robotic arm. This is a highly precise robotic arm that can handle complex tasks. Seven different tasks were tested during a realistic physics simulator to see how well the system could manage physical constraints and error in real time. These tasks involved interacting with objects in the robot's environment, and just like virtual home, feedback from simulators and controls helped guide error correction. We can see in the visual images how specifically this robotic arm was used to perform an uh, block arranging task. The authors have also released a video demonstrating this. Here it's being done without a feedback loop in place. Uh, Here there is a black block that needs to be grabbed, but it's not in the robot's working space. Now uh, this is the example where we have employed where they had employed feedback loop. So now without going to the black block, it went directly to the yellow cube, and it continued executing the tasks also. Now, for the results. In virtual home simulation, the brain body LLM showed a 29% improvement in task oriented success rates compared to other state of the art methods. On average, it completed 72% of all goal conditions across 80 different tasks. What made this system stand out was its ability to learn from raw simulator errors and update plans dynamically in real time. In real world tests with Francam, uh, the brain body LLM successfully handled complex tasks by incorporating feedback to correct errors during execution, which we saw in the video before. This further proved its robustness and adaptability. Overall, these results show that brain body LLM significantly improves task completion error rates and error handling compared to traditional LLM based systems. It's highly effective in both simulated environments and in real world robotic task planning. Thank you guys for watching.